We were discussing about the p-type and n-type semiconductor, and you know that in p-type semiconductor you have negative ions and positive holes, as mentioned here you can see, and in n-type semiconductor you have positive ions and electrons. Okay, so first of all I will draw the structure of p-type semiconductor. You can see this is the p-type semiconductor. In p-type semiconductor we have negative ions, so this is p-type. I am saying p-type semiconductor, you have negative ions, and you know that these ions can't move, so these are all negative ions and these can't move, and it has the positive holes. So the positive holes are like the chair, kursi, that means the electrons can come and sit there. So this is the positive holes. So these are all positive holes. Okay, next we have something like the n-type semiconductor. In n-type semiconductor you have positive ions. These positive ions can't move. Okay, that is very important. You have positive ions here. These positive ions can't move. This is n-type semiconductor. But in n-type semiconductor you have negative electrons, I told you. So there are a lot of electrons which is associated with positive ions, and these are all electron. Okay, and this is n-type semiconductor. Now what we have done, we have combined this. You can see these were separate. Okay, these were separate, this one is separate. Now we have combined this, so we are going to combine this. We are going to combine this thing. Okay, we are going to combine. So when we combine, you know, it will be combined like this, it will be combined like this. Now you can see on the left side, that means on the p-type semiconductor, you have more holes, right? You have a lot of holes here, and on the right side you can see you have more electrons. You have more electrons. Okay, more electrons. Since the concentration of the holes is greater than electron, or we can say that there is a difference in the number of holes on the right, number of electrons on the right side and the number of electrons on the left side. That means right side is our n-type semiconductor and the left side is our p-type semiconductor. Since there is a concentration difference, because of the concentration difference between the n-type and p-type in number of holes and electrons, there will be a phenomenon which is known as diffusion. Okay, diffusion. So there will be diffusion. Actually, you can see that there are a lot of electrons on the right side, that means the n-type semiconductor. What will happen, these electrons will jump and sit in the holes, and this guy will jump and sit in this hole. This electron also will jump and sit in this hole. Now you can see that all the electrons are sitting in the holes, and the charge of the hole is actually, the hole is positive and the electron is negative. When this is the hole, actually this is the hole and this is the electron. So when in the hole, you can see here like this is the hole and this is the electron. When the electron jump and sit in the hole, electron is having negative charge and the hole is having the positive charge. Now the hole is filled with the electron, so you cannot see no more holes there. That means the total charge at this portion, the total charge become 0. Okay, so what will happen now, you can see this electron has sit in the hole. Now what I am going to draw is that I am going to project this part that I am showing here. This part I am showing here. You can see now you can see here lot of ions only. You can see lot of ions and positive ions at this end, positive ions, and already the electron, this is there on the left side and right side and left side is already there, another atoms are there. So you can see here electron as the hole is filled with the electron, so the whole electron pair vanish. That means the whole electron pair vanish. Now you can see some ions only on the left side, negative ions. You can see negative ions, and here you can see positive ions. So lot of 3 negative charges are there, so you will get a negative charge here, you will get a negative charge here, and you will get a positive charge on the right side. And this negative and positive charge is because of the ions. Actually it is because of the ions. So you will get a negative and you will get a positive, because lot of positive is here and lot of negative is here. So you will get a negative and positive. But you can see again the number of electrons on the right side is much high. Okay, and whenever there is a positive and negative, you know that there will be a electric field which is pointing from positive to negative. This is the electric field. So this is the electric field which is pointing from positive to negative. Now you see here there are a lot of electrons on the right side and lot of electrons on the left side, holes on the left side, and the electric field is actually due to the ions and it is weak. Since the electric field is weak, what will happen? More number of electrons, actually this guys will jump from here and it will sit in the hole. More number of electrons will sit in the hole. Then what will happen? You have got now lot of you have got lot of a lot of ions. That means you have got a big negative here now, and you have got lot of positive ions here, because electrons escape from there and it is sitting in the holes. So electron hole pair will cancel each other. So now there is no electron, no holes in that position. So you have got lot of negative charges and you have got a lot of positive charges. So there will be electric field which is very strong electric field. You can say now it is very strong electric field. So you have got more electric field either. The electric field is more strong. Since the electric field is more strong, you can see here on the left side, that means on the p-type semiconductor, you have a big negative charge, and on the end side you have a big positive charge. Because of this, you can see here there are another electrons on the third level. You can see here there are a lot of electrons. These electrons, you can see these electrons, actually electrons are negative charge, and you can see here this is negative charge. Electrons are negative and the charge of the electric field is also negative. So whenever there are whenever there is a negative field, then what will happen? Electrons cannot come, because negative and negative will oppose each other. So these electrons can't jump, because the electric field is so strong. Previously it was not so strong, now it's become very strong. So this process will stop. Okay, so once this electric field becomes strong, once electric field become strong enough, the process of diffusion, I told you it is diffusion. This process is known as diffusion. The process of diffusion stops. Okay, the process of diffusion stops. Okay, now you will get a stable condition and you will get something like this. As I told you, this was the condition. You will get negative, 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 negative like this, and you will get positive, positive, positive. You cannot see any electron or holes at this side, but at this end you have electron, positive, and electron, positive and electron, positive and electron, negative and the holes, 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 negative and the holes. So you cannot see any no electron or no holes, only ions. You can see only ions here at this end. So this end, actually we will call this as the depletion region. Depletion region. So when we connect this p-n junction, we will get a depletion region which is about this width. Okay, so this is known as a p-n junction. That means we are connecting p and n type semiconductor. So this is known as a p-n junction, p-n junction diode. Okay, this is known as the diode. So this is known as the p-n junction diode. So in a diode, actually you have p-type semiconductor and n-type semiconductor which is combined together. But at the combining region, that means at this region, actually the electrons and the holes will come together and they will cancel each other. Electrons will come and sit in the holes, and so that on this region, actually you can see only the ions. That means you can see here negative ions and you can see here positive ions, and there is an electric field. Okay, so there is an electric field. Now we will see, okay, these holes I will show with red color, that's better. The holes I will show with the red color. Okay, now you can see this is the holes, this is the holes, this is the holes here. So we have only holes, and all other big things what I have shown there, actually positive and negative charges, are nothing but the ions. And this region is also known as this region without any free charges. So you can see during this region, that means in this region there is no free charges, no free charges. So this is also known as the space charge region. Okay, there are some charges but they cannot move, and these charges are nothing but the ions. They are not free charges, so no free charges are there. Okay, now what I am going to do, so this is known as the p-n junction diode. Okay, p-n junction diode, or simply we will call diode. Okay, now what we are going to do is, I can give a positive supply here. I am going to give a voltage. Okay, I am going to give a voltage. So this is the p-type semiconductor, p-type, and the other one, actually this is the n-type. So what I am going to do is that I am going to connect the p-type semiconductor. I am going to connect the p-type semiconductor with a positive battery, positive terminal of the battery, and n-type semiconductor with the negative terminal of the battery. Okay, negative of the battery. So what will happen, I am going to connect it. So this is the p region and this is the n. You can see here this is the n region and this is the p region. Okay, this is the p region and this is the n region. So at the n region I will connect the negative of the battery, and the p region I will connect to the positive of the battery. So this is negative and this is positive. So if I connect like this, I will call it as forward bias. What's the name? Forward bias. So this is the forward bias. So I am going to put the heading p-n junction diode in forward bias. Okay, in forward bias. Forward bias. Okay, this is what we are going to discuss now. Now what will happen if we connect in forward bias? Okay, in forward bias you have p-type and n-type semiconductor, and you are connecting the p-type semiconductor with the positive and n-type with the negative of the battery. Now you can see this is the positive charge and this is the negative charge. So what will happen, I will your negative voltage, you can see I am going to give the positive voltage here and I am going to give my negative voltage here. So positive here. So what will happen, the positive is seeing the holes, and you know that the charge of the holes we mentioned is holes are positive and electrons are negative, and you can see here negative here, and you see here the charge of this electrons, many electrons are here, and charge of the electrons is negative, and negative will oppose each other. So what will happen, due to this negative charge, due to this guy negative voltage, this electron will try to move like this, this electron will try to move like this. Similarly, this also will try to move like this. But you can see there is a electric field, that means there is an electric field that I have already told you. There is an electric field because of this. This is positive. See, yes, this I have already shown here. This is, there is an electric field here, and this electric field will oppose this flow of electron, oppose this flow of electron. That means the electrons which are going from right side to the left side, it will be opposed by the electric field at this end. So you have to give some more voltage. So if you give 0 volt, actually there is no current. If you give 0.1 volt, actually electrons will not move. If you give 0.1 volt, no current, I can say. Similarly, if you give 0.7 volt, at least in the case of silicon, suppose this is a silicon material, then if you give 0.7 volt, what you may get, that the electrons will try to cross this junction, because there is no charges here. The electron will try to cross this junction. The electron will try to cross this junction. So some electrons will come again here, 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 and from the battery the electrons are moving. These are the electrons, and these electrons are moving in this direction. You can see electrons are coming from the battery like this. So what will happen, these electrons are waiting here, and these guys will jump to this. This will jump here, these electrons will jump here. Jump means it is going through the wire, that's what I am saying. So the electrons are reaching here. Now you can see lot of electrons at this end, lot of electrons this end, because electrons are coming from the right side. That means from the N side to the P side, and since lot of electrons are there, these electrons will combine with the holes directly, okay, and some more electrons will come here. Again this electron will move here, it will move here, it will move here. Now you see you have a positive charge. This is a positive, it is a positive terminal of the battery. You have a positive voltage. What will happen, these electrons will be attracted by this positive voltage. The electrons will be moving here, so the electrons will move like this, electrons will move like this, and finally it will complete the circuit. So the electrons will be moving like this, and it will be going into the positive terminal of the battery. So what is happening is that in the forward bias you are getting a current, if you give a voltage which is greater than 0.7 volt. So what I am going to do is that you have a p-type semiconductor and you have a n-type semiconductor. What I am going to explain, if you connect the p-type with the positive of the battery, and the n-type, this is the positive, and the n-type with the negative of the battery, what is happening is that the electrons will start from the negative of the battery, and it can move through the electrons can move like this, and it can penetrate the depletion region, and it can reach the p-type semiconductor, and these electrons will constitute a current like current. And you can see this is the flow of electrons, and I told you electrons are moving here. The electrons are moving from the negative of the battery to the positive of the battery like this. Electrons are moving like this. This is the flow of electron. This is the flow of electron. So we can have a current direction. I told you about the current direction. The current direction is from the positive. This is the positive like this. The current will be going from positive to negative, because the current is defined as the movement of the positive charges, but there are no positive charges in the whole system. You can see that only negative charges are moving. That means the electrons are moving and the charge of the electron is negative. So we can assume that the current direction is opposite to the movement of the electron. And this p-type semiconductor is connected to the positive of the battery and n-type is connected to the negative of the battery. This configuration we will call it as forward bias. Okay, I already explained this. But you should give the forward bias voltage, this Vf should be at least greater than or equal to 0.7 volt if you are making the whole substance by using silicon. That means you are using silicon for making p-type and n-type semiconductor, silicon, that means Si. But if you are, the Vf should be at least greater than or equal to 0.7, 0.3 volt in case of germanium. Okay, germanium. So in germanium you need only small voltage. If you give a voltage of 0.3 or 0.4 itself, you will get a current. But in a silicon type semiconductor, if you are manufacturing the diode using the silicon, at least you should give 0.7 or more. Okay, so if you give 0.7 volt in silicon, then you will get a current at least. Okay, so you can see here, this is the situation. Now we will see another situation. That was the case of the forward bias. Now we will see the case of reverse bias. Reverse bias in PN junction diode. PN junction diode. Okay, reverse biasing. What do you mean by reverse bias? Just opposite to the previous thing. You have a lot of p-type semiconductor here and n-type semiconductor here. N-type semiconductor here. In n-type you have positive ions. You have positive ions in n-type semiconductor, and here you see here a lot of negative ions in p-type semiconductor. But in p-type semiconductor you have moving part, which is nothing but the holes. There are holes here, they can move. Ions cannot move, but holes can move. And in the other one you have a lot of electrons here. See, lot of electrons. Okay, now what I am going to do in reverse bias, I will connect my p-type semiconductor to the negative of the battery, and n-type semiconductor I will connect to the positive of the battery. Okay, just opposite to the previous situation. So this is p-type. So p-type is connected to the negative of the battery and n-type is the other side. That means right side is n-type. N-type will be connected to the positive of the battery. So this is positive, this is negative. So since I connected here positive, you can see it's a big positive here. This is negative, this is a big negative here. Now what will happen? You know that this positive charge on the right side, and this is electron. Electron is negative charge. So if you give positive, if you have positive and negative, then what will happen? You can see this electrons will be attracted to the positive. Electrons will be attracted to the positive. Similarly, this will be attracted to the positive. So there will be a force of attraction in this direction. That means this is the force of attraction. Okay, force of attraction in this direction. Similarly, you can see this is negative charge, and you can see here this is positive charge, the holes are positive charge, and this is negative charge. So you can see there is a force of attraction. Actually, there is a force which is the holes will be trying to move like this. The holes will be trying to move like this. So what will happen? All these holes will try to move like this. Okay, now I can redraw this circuit. I can redraw this. The holes can be moving like this, and holes will try to move like this, and the electrons will try to move to the opposite direction. You can see here the holes. I will show only the holes. The holes will come and accumulate at this region. Next, because of the negative charge and because of the positive charge, the electrons will come and accumulate in this region, and you can see the width of the space charge region become more. That means width become more. Width become more means what? In the space charge region, only ions will be there. There is no charges actually. You can see here, this is the positive, 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 and this will be positive, 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 right? Similarly, you can see something like the negative, 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 negative. Okay, this is negative, 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 negative. You can see here all the electrons, all the holes from here actually move to this area. Similarly, all the electrons from at this end actually moves to the other area. Now they are free. These are all ions. These are just ions. Ions. So only ions are there at the junction, actually near the junction and other region. So you have lot of holes, you have lot of electrons at the other end, so that electrons and the holes are not crossing the junction, or it become more difficult for them to cross the junction. So no current, actually no current. No current. That means they cannot move or cannot cross the junction. Can't cross the junction. So because of that, there is no current. So this will happen in the case of reverse bias. So I am going to conclude it. So in the reverse bias, if you have a p-type, n-type, in the reverse bias, you are going to give the negative to the p-type and positive to the n-type. Actually, the electrons will try to move like this and the holes will try to move like this. Okay, so actually no current. So this is the case of reverse bias, RB. RB means reverse bias. But in forward bias, I told you, that means FB means forward bias. Okay, not Facebook actually. So it's forward bias. So you have p-type and n-type. To the p-type you will give positive, and to the n-type you will give the negative. Okay, so what will happen? Because of the positive and negative here, this guy will push the holes like this. Okay, and this guy will push the electrons like this. This is the holes and this is the electrons like this. So they will combine, and the electrons finally move here through the wire. Okay, so they will combine. So electron has some chairs. That means chair is hole. So electrons will be moving like this. Okay, so electrons will start from the negative terminal of the battery and it will move like this. So there will be a current in the opposite direction. So this is the movement of electron. This is the movement of electrons. Okay, this is the movement of electrons. So electrons are moving in the anti-clockwise direction as shown here. So the holes are moving in the clockwise direction. So we will always say the direction of the current will be the direction of the movement of the holes. So the holes will be moving and coming like this. That means holes are positive charges. So you are getting a current. So this is the current direction. So what for silicon, I told you the forward bias voltage, and this is the reverse bias voltage. Anyway, the forward bias voltage should be greater than or equal to 0.7 volt. So should be greater than or equal to 0.7 volt in the case of silicon. Okay, in the case of germanium, it should be greater than or equal to 0.3 volt in the case of germanium. So in forward bias, I told you the positive is connected to the p-type is connected to the positive and n-type is connected to the negative. But in reverse bias, as I told you, the p-type is connected to the negative and n-type is connected to the positive of the battery. So in reverse bias, no current. In forward bias, you have current. And here no current. Okay, so that is the difference. So we have studied two types of biasing techniques, which is forward bias and reverse bias. Now I want to tell you the symbol for the diode. Okay, suppose you have a p-type semiconductor and this is the n-type semiconductor. This is simply the diode, but we have some circuit symbol for this. In circuit diagram we have to show it by using some symbols. So circuit symbol, you know that resistor is shown like this. This is the resistor, this is the capacitor, and this is the inductor. Like this, for the diode we have a symbol which is like this. Okay, I am drawing it big actually, and this end is the p-type semiconductor and this is the n-type semiconductor. You can see here whenever there is a current, the current is flowing from, the holes are moving like this, as I told you. So the current is moving from P to N. So you can see that the current moves only from P to N. That means you have something like this. So the current will be moving in this way. That's what I am saying you. This is the direction of the current. Okay, the direction of the electron is opposite to the flow of current, that I have told you already. You can see the electrons are moving in the counterclockwise direction, but the current is moving in the clockwise direction. So you can see that there is an arrow here. This is showing the direction of the current actually in forward bias. So the current will be there only during the forward bias. So this is the symbol for diode. So this end is the p-type and the other end is the n-type. So the current will move only in this direction, and you can see there is a blocking. That means in this direction there is no current. The current in the opposite direction is 0. So 0 ampere current actually in ideal case. So that is the situation of a diode. I hope it is clear to you, right? Now we will see various models for the diodes. So we will see diode models. It's very, very important. Okay, diode models. So first of all, we will see the practical model for the diode. It's very, very important. The practical model means we will consider two cases, the forward bias and we will have the reverse bias. And this is my circuit. Actually this is a diode, this is p-type and this is n-type. So I can connect a voltage like this. Okay, I will show it in the forward bias region. You can see here I can connect like this. This I can connect with a positive and negative. Okay, this is p-type and this is n-type. And in the reverse bias I have the diode like this. This is p-type and this is n-type, but for the p-type I will connect the negative, and for the n-type I will connect the positive. Okay, this is positive and negative, this is negative and positive. So both are there. Now we have forward bias and reverse bias. Now in the practical diode model, I told you need to apply is voltage at least greater than 0.7. But usually when we connect a diode, we want to limit the current. If we allow any current through the diode may damage. So we usually connect a series resistance with the diode, and this resistance is known as R. And here also I can connect a series resistance with the diode, which is known as R. It is to reduce the amount of current. Okay, it is to reduce the amount of current. Now when the diode become forward bias, you will get a voltage across the diode. The drop will be across the diode, that means 0.7. I told you the diode will not allow until you give 0.7. Suppose if you are giving a 10 volt, the diode will allow 10 volt. But the voltage across the diode due to that electric field, actually it is that you are opposing is actually 0.7. So the voltage across the diode in forward bias, it will be only 0.7. Okay, suppose you are giving here 10 volt, the diode will consume 0.7 only, and what will be the voltage across the resistor? The resistor will take the remaining voltage 9.3. If you don't put the resistance, the current through the diode will be very, very large, and finally your diode will damage. So we can draw the model for the diode like this. So in the forward bias, the diode is showing a voltage of 0.7. So plus minus, you can see here it's plus and minus. Okay, sorry, this is minus is here, plus and minus. So I can draw the figure for the diode like this, plus and minus. Here you are applying the positive, and the diode is acting as a short circuit. Why it is a short circuit? Because you are giving the positive of the battery here. This is the positive of the battery, and this is the negative of the battery. So these are batteries. Okay, battery symbol actually. So this is your diode model. The diode is acting like a short circuit. That means there is a current. In forward bias, the diode act like a short circuit. That means the diode constitutes some current, or it allows some currents. So the voltage across the diode I have to show here, that is 0.7. Now we will see in reverse bias. In reverse bias, the diode will never conduct. So in reverse bias, no current, actually no current. So we can say that there is no current through the diode. So in reverse bias, you will apply the negative voltage here, and you will apply the positive voltage. Okay, that means this end here it is the p type part, and this end here it is the n type part. Similarly, this end you are giving the negative voltage, and this end was actually this end is actually the n type, but to the n type you are giving something like this is the battery anyway. Okay, so what I want to show is this end is the p type semiconductor, p type, and here this end is the n type semiconductor. So here this is on the right side, you can see p type and n type, and there is no current through the diode, and the diode is an open circuit. That means the diode is open circuit. Okay. So this SC here, this is open circuit. Okay, OC means open circuit, and SC is short circuit. Okay, SC is short circuit. So no current. So this is the circuit equivalent. So if we have a diode in our circuit, and if the diode is forward biased, then we can immediately remove it. Suppose you have a resistance, you have a capacitor, okay, you have a diode, and you apply some voltage. Example, you apply some voltage which is positive and negative. Then you can have the same circuit like this. This one you can replace in place of the diode. In place of the diode, you can see this positive is connected to the P and negative is connected to the N. So the diode is, you can replace the diode with a positive negative 0.7 volt in the case of a silicon, and you have a short circuit. Not this is open circuit, short circuit. This is short circuit. Now you can draw the remaining part of the figure. Now the circuit analysis become more easier. Okay, so you can change to this form by using, this is the practical diode model. Okay, now if you have something like this example, you have an inductor, the diode is connected in the opposite way. The diode is connected to the opposite way, and you see here positive, negative is connected to, this is the N, this is the positive region, and this is the negative N region. You can see here it is reverse bias. So in reverse bias the model is different. I told you in the reverse bias it is acting like an open circuit. You can see this is the model. in reverse bias. Okay, in RB it is the model. So you can see it is an open circuit. So I can do like this. It's an open circuit. So the diode can be replaced with an open circuit. Okay, this is the open circuit, and I can draw the remaining. So no current will be there. So this is how we can use this model for evaluating. This is changed with the open circuit because it's reverse bias, and previously I have changed this guy with this one because it is forward bias. Okay, so that's what the model says. Okay, now we have one more model, two more models. Before that we will see the ideal model. Okay, the ideal model. We will see one thing known as the ideal model. So in the ideal model, actually we have the same condition like this: forward bias and reverse bias. So what do you mean by the forward bias? Forward bias means positive. This is P and this is N is connected to, and you have a resistor, current limiting resistance, positive and negative. Okay, and in the reverse bias you have the diode like this, but you will change the battery condition. That's it, and you have the resistance R. Okay, so in R is actually not required in reverse bias because there is no current anyway, but we, for safety reasons, we usually used to put R. Okay, so you can see it is reverse bias. So in ideal model, actually we will say that in the forward bias situation, your diode will simply act like a short circuit. There is nothing like 0.7. That means 0.7 is omitted. We remove 0.7. Your diode is very perfect. So that means actually it is not perfect. I told you that in practice, if you give a voltage of 0.1, it will not conduct actually. But in ideal model, we assume that your diode is perfect and it doesn't require 0.7. No need to cross the boundary of 0.7. Okay, even though if you give 0.1, it will conduct. That is an assumption. It is an ideal diode model, and it is used for getting reasonably simple approximation. That's it. So you can see that 0.7 is omitted. So the voltage across the diode, now I am saying during the conduction, the voltage across the diode, I am saying it is 0 volt. That means diode is very perfect. It doesn't require 0.7. So nothing like the silicon or germanium, whatever. That means 0.7 we are omitting. Okay, so diode is acting like a short circuit. However, in reverse bias, you can see here there is no current in reverse bias. So in reverse bias, it is simply open circuit. That's it. Like same previous situation. So if you have a circuit like this with a inductor, you have a diode, and if you are assuming the ideal model for the diode, you see here positive and negative. I can replace this guy with inductor. This is short circuit, and like this. So I can replace the diode with a short circuit. That's it. Similarly, I can have open circuit if I am connecting my diode like this. And I connect the positive here and negative here. Okay, you see here this is reverse bias. Previously it was forward bias. So I can replace this with an open circuit. Okay, this open circuit, and this is my battery. I would show the battery. Okay, that's it. So this is how, by using the ideal model. Okay, this is the ideal model, using the ideal model. So this is an example for using the ideal model. Next we have last model, which is known as the complete model. That is the perfect model actually. Practical is also good model, and the ideal is okay, it's approximation, but practical is more accurate. Okay, so we have last model, which is known as practical model. So we have same like the previous situation, forward and reverse bias. So in forward bias I have a diode, I have a resistance, and I connect positive and negative like this. In reverse bias I have the diode, but I change the power supply, negative and positive like this. Actually there is a current here, and here no current actually. So what I am saying is current. Okay, this is the current. Here no current, but we will see something in more detail. we will assume our diode, we will change our diode. This is our diode. So this diode I will change with the same thing as 0.7. Previously in the practical model I was using a short circuit, but it is not a short circuit only. You have some more thing. You have the resistance for the diode. The diode will show a small resistance actually, like your the diode will be is not perfect. The diode is having a resistance. So diode is having 0.7 volt here. That means you can see a 0.7 volt and a resistance RD dash. That means there is a resistance RD dash. That's it. Okay, that's it. Now I can give an example here itself. Example, you have a example I will give it in the next page. Similarly, in the open circuit, actually in the reverse bias, you have the diode like this. You have the diode in reverse bias. In reverse bias, actually you have the open circuit. Okay, this is the open circuit in reverse bias, I told you. But the diode is not perfect. It is something like a valve. For example, you know that in the wash basin in hammam you will be using the water tap. If the water tap is not perfectly closing, if it is perfectly closing, you will not get any water actually if you are closing it perfectly. But if the water tap is having some complaint, then if you close it also, you will get some drops of water, like the drops of water will come. Some drops of water will come like this. Very small drops of water will come. That means you will have a leakage. There will be a small current which may go from this positive to negative. Very small current of microampere, which may go from positive to negative. That means it will go from N to P. If the water tap is like water tap example, as I told you, if it is not perfect, even though if you close it, some water will leak, and we will call this as leakage current. So leakage current will be flowing, but there is no path for the leakage current. You can see it is open circuit. So I have to show the path for the leakage current using some resistance. So this resistance, it is RR dash. Okay, it is it's a very huge resistance which may flow, and this resistance actually it is usually shown as RR dash. It's not like this simple. Usually it is denoted by RR dash like this. So it is a reverse resistance. So it is a reverse resistance, and I told you that the current is very small. So this will be in the order of mega ohms. Okay, and here I told you this guy, that means RD dash, it will be of the order of ohms. That means example, I can say example some 8 ohms, 6 ohms here. But this guy actually RR dash, this is the case of RD dash, and RR dash is very high, maybe something like some 10 mega ohms, 20 mega ohms like this. Okay, this is the example. So it is very high. So this is the practical model, I can say practical model. Okay, so that's a practical model. So I can give an example now. You have a diode circuit with R, L, and you have a diode now. You see here the diode is forward bias because positive is connected here, positive. That means P, and this is N is connected with the negative. That means your circuit is forward bias. So I can replace the diode with 0.7 and a small resistance RD dash. It will be usually given. Okay, next, the remaining thing you can draw. That's it. Okay, this is the model, actually complete model. Okay, next we can have one more example for the reverse bias. This is what's for the forward bias, and this for the reverse bias. For the reverse bias, same circuit R L, but I am changing the diode direction. Okay, that's it. Now I can change this diode model. I can use the diode model R L, and the diode is open circuit. I told you the diode is open circuit, but there is a leakage. Leakage is R dash. This is the leakage. Next, I have the remaining part, positive, negative. That is. So I have a path for the current. Actually, the current will flow like this. It will be flowing like this. Okay, this is the direction of the. But this resistance is very high, of the order of mega ohm. The current we will call reverse current. Okay, the current which is called as reverse current, it's very small. Okay, the current is very small. Reverse current, we will call this current as the reverse current. Okay, so these are all the different models, and the forward current of the diode can be given by using one equation that I want to tell you. So the reverse current is the current, actually, what is that reverse current? Reverse current, we will call it as IR. It is the current in reverse bias. It is a small current in reverse bias. In ideal model and the practical model, actually we assume that the reverse current is 0. That's why we didn't provide any path for it. But the reverse current is a very small current, and we will see only it in complete model. That is the actual case of the diode, actually. Small current in reverse bias. Okay, that is the reverse current. And the diode equation, I will give the diode equation. Basically, the diode equation, the forward current will follow this equation, which is IR into e power Vf by eta Vt minus 1. Okay, this is usual. And Vt is given by K is the Boltzmann constant into Tk divided by Q, where Q, you know, it's 1.6 into 10 power minus 19 coulombs, and Tk is the absolute temperature in Kelvins. Okay, and K is the Boltzmann constant. Okay, this is the diode equation. You can find the diode current. So the actual diode current will be like this. It will be having an exponential behavior like this. Okay, this is the actual diode current. So we will see some more details regarding our ideal, practical and the complete model. So we will see something like in the practical model. In the practical model, in forward bias and reverse bias. In forward bias, I told you in the practical model it's 0.7 and a short circuit. Okay, so the current will be only conducting only, this is P and this is N. So the current will be conducting only if you give the positive voltage. Okay, so positive voltage of 0.7. So you will be getting a current of 0.7. Till 0.7 there is no current, and the current will be going high. Okay, short circuit. And in the reverse bias, I told you it's open circuit in the reverse bias. it's open circuit in the reverse bias. That means no current. So the current is 0 in the reverse bias in open circuit. Okay, this is the situation. Now we have the ideal model. Ideal model, this is the characteristics I am showing. This is the voltage and the current characteristics. So I am drawing the voltage and the current characteristics. Voltage and the current. So in the forward bias, I told you, as I told, it's positive, negative here. In the ideal model, it's short circuit, and in the reverse bias, I told you, it's simply open circuit. So in the forward bias, even though if you give something greater than 0 volt, you will get a current like this, short circuit. And in reverse bias, I told you it's open circuit, so no current is 0. So this is open circuit. So this is the forward and reverse. Okay, this is the forward bias, and this is the reverse bias. Similarly here, this is the reverse bias. Okay, and this part is showing the forward bias. Okay, next we have the complete model. So we have the complete model. What is that complete model? In the forward bias, you have 0.7 and a small resistance RD dash, short circuit but with a small resistance. This is 0.7. This is P type and this is N type. And in the reverse bias, I told you, you have an open circuit, but there is a leakage current which is through the resistance RR dash. So I am going to draw the figure. You have the voltage and this is the current through the diode. Now the resistance is there. You can see a resistance in the forward bias. So in the forward bias, you have the current only after 0.7. That's what the 0.7 means. After that, there is a resistance. Whenever there is a resistance, you have a slope, and the slope of this is 1 by RD dash. That is the slope of this. And in the reverse bias, I told you there is no current actually, but there will be a small current due to this. The current will flow like this. This is P and this is N. The current will flow from P to N like this. So this is known as the reverse current IR. Reverse current, which is very small. That means of the order of microampere. So this is the current. You can see it's small current, and it is having a slope actually 1 by RR dash. That is the slope of this curve. Okay, since R is very high, the slope 1 by R dash will be very, very small. Okay, it's small current. That is the reverse current. So this is about the complete model. So we have seen different types of models for the diodes, like practical model, ideal model, and the complete model. I hope you understand. Next, actually, we will discuss, we will do one problem with this, and after that we will start the different applications of the diode. Okay.